I'm Jose, and I'm the developer of Becas.
Hi, I'm going to make a short presentation about Becas, the beam cross-section analysis software developed at VIM, the DTU Wind Energy Department. This is work developed by me and some co-workers. So essentially Becas is used for the structural design of wind turbine blades, and I'll try to briefly describe the workflow we have developed using Becas. So here on the left, you could imagine that you have a model of the blade. This could be drawings or a shell element model, and you're interested ultimately in representing this blade inside some air elastic model. So what we propose is that you choose a section of your blade of interest. This is the cross section, which you mesh, and based on each mesh you can generate the cross section stiffness properties and then generate a beam finite element model that represents the original section of interest. You do this along the whole blade, and then you just fit it there as beam finite element models representing the blade in the air elastic model. So this is the first use of Becas, as you can see, as a pre-processing step before entering the air elastic analysis tool. Then you can also use it again now as a stress recovery second analysis, where based on the loads that you calculate from the air elastic analysis, you can go back to the cross-section finite element mesh and determine the stresses, or some recent work we've done includes also crack and fracture analysis. So in essence, the specifications and capabilities, we have a finite element based tool for analysis of cross-section properties. The idea when we developed this is really to improve the accuracy of these beam models, especially on the blades where you have complicated geometries and many types of materials. So in fact, Becas is able to estimate or to account for the effect of material anisotropy and inhomogeneity. And we have validated extensively the results from Becas to match. We can verify that they match 3D FE models, although we use only a fraction of the computation time because of the efficiency of the beam models. This is an open source MATLAB tool. It's free for academic use, so if you are sitting at any university or research institution, please go to becas.dtu.dk and contact us. For commercial users, you can always contact us and we make it available upon a small fee, also the source code. So to finalize, I'll just go through some of the work we have done using Becas. We have recently finished designing the DTU 10 megawatt reference wind turbine blade, where we essentially cut out many slices from a shell model, as you can see here, and then we do a very fine representation of the blade within the beam finite element model, which is then put into HOP2, our air elastic code. This is an example of the strength analysis on the detail stress analysis in the corner here of the spar and shear web connection. And you have a comparison here between the results from Abacus and Becas, and you can see there's a very good match. We have recently also concluded implementing some failure criteria specific for laminated composite structures, maximum stress, maximum strain inside. We have in the past, and now this is some ongoing work also using this for topology optimization of wind turbine blades, where we are interested in defining a domain, which is the cross-section, and distributing the material herein. The interesting thing is really to explore the fact that the beam model is so much more efficient to include air elastic constraints, which using 3D models is not possible. Finally, the last work we have done is on fracture analysis. So we use the virtual closure, crack closure technique to calculate strain energy release rates on cracks in the cross section. And once again, we see a very good match with 3D results for all three crack modes.
Hi, I'm Robert, and I'm a member of the Becas team.
I'm going to show you some of the pre-processing capabilities that come with Becas. We will be using a Python script called shellexpander.python, which can read information from a finite element shell model describing, for example, a wind turbine blade, and based on the information found there, produce a series of Becas input files. In our case, we will be reading information from a file called refblade.input, which is an Abacus shell model. Let us have a look at this model first. So here is the model of our wind turbine blade. It contains a number of element sets that corresponds to sections that Becas should analyze. If we look at these sets, we can see that they run through the blade. Now if we look at one of the sets only, we can see something like that. And each of the elements in such a model contains information about ply thickness, material orientation, and geometry, all that we need to produce our Becas input files. So let us run Shell Expander. We do that by calling the Shell Expander script here in the command line. We type Python shellexpander.python, and as a parameter we give it an options file which stores information like where to read information from, where to write it to, how many elements to use, and so on. The script is now running. It will be generating Becas input files to analyze 9 cross sections. In reality, you would of course use more, maybe something like 50 cross sections to analyze a wind turbine blade. The script is finished and a new directory has been created, which is called Becas input. In this directory, we see 9 subdirectories corresponding to the 9 cross sections, and in each of them we find the Becas input files. Now, running Becas itself is done by running a MATLAB script, which calls functions which are defined by the Becas toolbox. For example, here is a function computing the cross-section stiffness matrix, or here you can see the function that then computes the cross-section stiffness properties based on that. We hit F5. The script runs through the 9 directories and computes the 9 Becas models. This takes a few seconds. Now we're done, and in our Becas directory we now find some new files. For example, a file containing the cross-section stiffness matrix. This is what you see here. Or also a plot showing the mesh that was generated by Shell Expander, and also the centers computed by Becas, and also the orientation of the principal axis. Last but not least, Becas has also computed cross-section stiffness properties and converted them to HOG2 format, and the result of that is stored in this file becas2hog2.out. So this data is ready to be included in HOG2, DTU Wind Energy's aeroelastic code. Of course, this approach is not limited to Abacus model, but with slight modifications, you could use any kind of finite element shell model. For more information, please visit www.becas.dtu.dk.